Electrical power generation relies on physical rotation. Because turbines spin, the resulting voltage and current don't push forward in a straight line. They exhibit a cyclic reversing behavior, pushing and pulling electrons through a circuit in continuous waves. This animated graph plots that behavior over time, modeling it with the basic equation, V of t equals V max times the sine of omega t. Measuring the raw amplitude of this wave gives us two immediate metrics. The distance from the baseline to the crest is the peak voltage, and the total vertical drop from the crest down to the trough is the peak-to-peak voltage. But determining how much actual energy this wave delivers presents an immediate mathematical problem. Because the waveform is perfectly symmetrical, the positive area above the baseline exactly cancels the negative area below it. Over one complete cycle, the standard arithmetic average of this current is exactly 0. To calculate a mathematically useful average value, we must strictly integrate the wave over exactly 1/2 cycle, bypassing the negative cancellation. For a pure sine wave, this integration yields a constant average of 0.637 times the peak amplitude. While accurate for a half cycle, continuous fluctuation renders a simple total arithmetic average useless for practical engineering. We need a statistical equivalent to accurately measure a continuously alternating system's actual capacity to do work. That equivalent is the root mean square, or RMS. The RMS value of an alternating current is strictly defined as the exact equivalent DC value that would produce the same heating effect if passed through a given resistor. Looking at these comparison circuit diagrams, deriving that value starts by squaring the instantaneous values of the AC waveform. By squaring the function, all negative values become positive, eliminating the cancellation problem over a full cycle. Panning down to the integral equations, we take the mathematical mean of those squared values over one complete cycle, and then extract the square root of that result. The final solved fraction proves that for a pure sine wave, the root mean square voltage is exactly 0.707 times the peak voltage. This specific calculation is so crucial to grid infrastructure that standard voltmeters and ammeters are calibrated to display the RMS value exclusively, ignoring the peak amplitude. To categorize different wave shapes, engineers divide this RMS value by the half-cycle average value. This ratio is defined as the form factor, allowing us to compare the power delivery of non-sinusoidal waves, like square or triangle waves, against a standard baseline. A secondary metric, the peak factor or crust factor, is calculated by dividing the peak value by the RMS value, indicating how extreme the wave's maximum spikes are relative to its baseline power. The RMS conversion mathematically translates fluctuating variables into stable constants, making reliable power calculations across AC networks possible. With a stable measurement established, we have to address how different components process that energy. In a series RLC circuit, resistors, inductors, and capacitors react to alternating current differently, introducing delays. This graph charts voltage and current across time. When AC passes through a pure resistor, the instantaneous voltage and current pulse completely in phase. They crest, fall, and cross the zero line in perfect synchronization. A pure inductor, however, resists changes in current. This creates a time delay, forcing the voltage to peak early. The voltage wave now leads the current by exactly 90 degrees. A pure capacitor does the opposite, resisting changes in voltage. This causes the voltage to lag the current by exactly 90 degrees. This creates a rigid geometric reality. Because the inductor pushes the voltage 90 degrees forward and the capacitor pulls it 90 degrees backward, inductor voltage and capacitor voltage are exactly 180 degrees out of phase with one another. Attempting to calculate the total energy of a circuit containing multiple out-of-sync sinusoids using standard time domain calculus creates a massive mathematical bottleneck. The equations become long, complex, and prone to error. To solve these circuits efficiently, the system must be mapped out of the dimension of time and translated into a dimension of static geometry. We achieve this geometric mapping by using complex numbers to represent time-varying sinusoids as fixed points on a two-dimensional mathematical plane. In mathematics, the lowercase I represents the square root of -1. In electrical engineering, we use the letter J to avoid confusion with current. But while J represents an imaginary number mathematically, its physical function here is an operator that dictates a specific geometric rotation. Looking at this vector rotation reference, multiplying any vector by J forces a 90-degree counterclockwise rotation. Consequently, multiplying by J squared rotates the vector 180 degrees, perfectly modeling the opposition between inductors and capacitors. This top graph plots a complex number in Cartesian or rectangular form. Written as z equals x plus jy, it defines a precise point on a two-dimensional grid. Here, the horizontal x-axis represents the real, active component of the circuit. The vertical y-axis, multiplied by our rotational j operator, represents the imaginary or reactive component. Panning down to the triangle diagram, we see the polar form. It identifies the same point using a vector's total length, a, and its angle from the origin, theta. Converting between these forms relies on basic geometry. The magnitude A is found using the Pythagorean theorem, the square root of x squared plus y squared. The angle theta is found using standard trigonometry, taking the inverse tangent of the y divided by the x. We can also find the conjugate of any complex number, which simply retains the exact same magnitude A, but flips the positive or negative sign of the angle theta. By locking time-based phase shifts into fixed angles on a plane, engineers can add, subtract, and multiply the interactive forces of an AC circuit using basic algebra, sidestepping the need for advanced differential calculus. With the complex plane established, we can mathematically define the total opposition to alternating current flow. We call this complete vector impedance, symbolized by the letter Z. In this microscopic visualization of electron flow, the real part of the impedance vector is pure resistance. The imaginary part is reactance, an inertia against electron motion caused by the magnetic and electric fields of inductors and capacitors. We also define the exact mathematical inverse of impedance, called admittance, and symbolized by Y. It measures exactly how easily a circuit allows current to pass through. Admittance is also mapped on the complex plane. Its real, horizontal part is conductance, and its imaginary vertical part is susceptance. Every physical component added to an AC grid alters the length and angle of the Z vector. That final mathematical coordinate dictates exactly how efficiently the source voltage can push current through the system. While instantaneous power is defined simply as voltage multiplied by current, the phase delays introduced by impedance mean that total circuit power cannot be calculated with a simple scalar multiplication. These trigonometric product-to-sum equations prove that multiplying out-of-phase sinusoids results in two distinct terms. A single phase shift forces the circuit to exhibit two separate power behaviors simultaneously. Watch this power triangle construct on screen. The hypotenuse represents apparent power, symbolized by S. Measured in volt-amperes, it is the raw mathematical product of the RMS voltage and RMS current. The horizontal base represents real power, symbolized by P. Measured in watts, this is the actual energy consumed by resistance to perform tangible physical work. The vertical side represents reactive power, or Q. This is phantom energy. It continuously oscillates back and forth between the source and the reactive components, doing exactly zero real-world work. The internal angle separating the apparent power from the real power is theta. This angle is the ultimate metric of the circuit's efficiency. Taking the cosine of theta gives us the power factor. It is the direct ratio of the real power doing work against the total apparent power mathematically present in the lines. A lagging power factor indicates a heavy inductive load, where current trails voltage. A leading power factor indicates a capacitive load. In either case, the wider the angle, the less efficient the system. Mastering alternating current requires translating time-varying sine waves into RMS constants, mapping phase delays into complex vectors, and calculating the resulting impedance. Every step in this architecture exists to control this final phase angle, ensuring that mathematical oscillations are efficiently converted into maximum.
Thanks for watching, and please like, share, and subscribe for such more content and appreciation. Make sure to comment your questions and